For this lesson, we're going to look at infinite limits. So these are the limits that are going to approach infinity or negative infinity, depending on the value of the function. We've already talked about when values do not exist, and for the most part, this is what we're dealing with. We're looking at where values are undefined. So we've already seen if we have some limit as x approaches some value, let's say how about 2 of something that looks like this, and if I do direct substitution for this particular problem, I'm going to get 0 over 0, which gives us our indeterminate form, which means we can do something with this, factor it or whatever, in order to end up with an actual limit. And in this case, again, this is review here. So if I'm looking at this here, I would factor this difference of squares, x minus 2. And then I'd end up with that, and then I can direct substitution because those factors cancel, and I end up with 4. So even though this function is undefined at x equals 2, because I get a 0 on the bottom, I can still find the limit by these other methods because I get 0 over 0. Now most often we're going to get infinite limits when we end up with, instead of 0 over 0, we get some number over 0. So let's say I want to find the limit as, let's say, x approaches 4 of a function like this, 3 over x minus 4. Now if I do my direct substitution, I'm going to get 3 over 0. Still undefined, but this isn't our indeterminate form, so I can't do any special sort of factoring to this to make this, we would say this limit does not exist. But I can look at the one-sided limit to determine what direction this is headed in. So let's say I look at the one-sided limit as x approaches 4 from the left. And if I think about this numerically, I'm thinking about values on the left of 4, such as, well, let's get something very close, like 3.99. If I plug that in there into my function, I'm going to get a negative value on the denominator. It's going to be a negative small decimal. And as I get closer and closer, okay, the closer I get to my 4 value from the left, the smaller this decimal becomes. So I get a really, really small decimal here, and it's still negative because this 3 value is less than the 4. So we get a really, really small decimal. Well, if I take a number like 3 and divide it by a really small decimal, the value of this is going to keep getting larger and larger the closer I get to 4. And so what happens is this eventually ends up going to negative infinity. So what we end up with is 3 over a very, very small negative decimal, almost like saying negative 0.000 and so on. And so the smaller this denominator is, what ends up is this function at 4 ends up curving down towards infinity like that, towards negative infinity. So we say this limit approaches or goes towards negative infinity. And if I look at the other side of if I look at the right side, well, the limit of this as x approaches 4 from the right, I'm looking at values like 4.000001 minus 4, after I plug in. I realize I'm plugging it in here. So we end up, again, a very, very small decimal, very close to 0, but it's positive. So a positive to positive, this ends up heading towards positive infinity. And so it ends up going like this. And so what we end up with here is at x equals 4, we've got basically ourselves a nice little asymptote here. We've talked about asymptotes before. Okay, so whereas before when we had 0 over 0, that ends up being a hole in our function. If I have a number over 0, that gives us an asymptote. So to sum that up, if I have the limit as some x approaches whatever, some c value of a function, if this ends up being 0 over 0, okay, this gives us a hole in the function. Where it is not defined at that x value, and we have to do something else to find the limit. If I'm looking at some limit as x approaches some x value of f of x, if I end up with a number over 0, well, this is where we end up with an asymptote. And so then it makes it very easy to tell the difference, or how to find which one, because I end up with a, for whatever values that's undefined, if I can cancel that out, that factor out in the top, we end up with a removable discontinuity, whereas on the bottom it's non-removable and it's an asymptote. For example, let's look at a problem like, something like this. Let's say I'm looking at f of x equals x squared minus 1 over x minus 1. Okay, now we know this can simplify here. To x plus 1 and x minus 1. So the value is not defined at x minus 1, but since it'll cancel out, we don't end up with an asymptote here, we end up with a hole. Well, we end up with a hole when x is 1, and if I plug that back in, once that cancels, if I'm looking for the limit as x approaches, erase that, as x approaches 1 of this, well, it's the same as the limit as when x approaches 1, since that canceled, of x plus 1, which would equal 2. So we'd have a hole there, because remember 2 would be our expected y value. Okay, so this would be a removable discontinuity when x equals 1. Let's look at another example. Let's say I have something like this. Let's mix it up. Let's call it g of x equals, x squared plus 2x minus 8 all over x squared minus 4. Okay, so let's factor this fully. So if I factor this, I've got a trinomial on top. This is where it helps if you're able to factor quickly. Okay, I can put x and x because my leading coefficient is 1. I'm looking for the factors of negative 8. I'm looking up here now. factors of -8 that add up to a +2. So that's going to be a +4 and a -2. And then the bottom, this is the difference of squares. So this will be x plus 2 and x minus 2. Okay, and so since these are common factors here, those are going to cancel. Well, I'm going to end up with, at -2, I can plug that in. So I'm going to end up with an asymptote for this factor here at x equals -2. And then I can determine whether on either side of -2, whether that's going to approach positive infinity or negative infinity by just plugging in and looking for signs. And then there's going to be a hole when x equals +2, because that's able to cancel out there. And so a hole, we call that one removable. That's a removable discontinuity. And the asymptote is going to be a non-removable. Removable. Don't mind the sloppy writing. You heard it. You write it better. Okay, so we got removable versus non-removable. And that's about it. So give those a try. There's some other problems in your book you can look at. And got a little assignment for you. We got page 88, 1 through 49 odd, and 59 and 61. Do well, and we're about done with this unit. We'll look at taking a test next week.